The robots are literally getting more powerful, and that's changing the electronics inside of them. Modern robotics designs are moving away from the classic 12-volt ecosystems and up to higher operating voltages, which means different battery management, different motor drivers, and different chipsets under the hood. And that's what we're exploring in today's Tech Chat, sponsored by Mouser Electronics. I'm Daniel Bogdanoff, and I'm joined by Aaron Barrera, Strategic Marketing Manager for Motor Drivers at Allegro Microsystems, to explore the world of higher power robotics in industrial automation. Aaron, thanks for being here. I'm really excited to learn more about this.
Yeah, I'm excited as well.
It seems like the world of robotics and power robotics and industrial automation is changing a lot. We're seeing voltages change. We're seeing potentially a lot more of it in the world around us. What are some of the things that people who are unfamiliar with this space might be surprised by?
Yeah, great question. So, robotics is a very intriguing space because you have a lot of robotics being used by companies to automate and have their businesses be more efficient. And as the world has a lot of changing requirements, you have things like higher payloads, needs for higher integration and efficiency so that you can lower electricity bill costs, but also get more done on a day to day basis. So there's really interesting design challenges that need to be solved in the world of robotics that directly impact how manufacturers are addressing these types of solutions in the semiconductor world.
What are some of the macro trends you see in the world of robotics? Is it all power related, or is there more going on than that?
Great question. So when you look at smarter power, this means efficiency. For the power that I'm putting into my system, am I getting all of that power out? Because if you're not, then you're wasting power, and this can lead to higher electricity bills, more thermal losses, things like that. So the best way to address smarter power is how can I get more efficient systems in robotics? And a great way to solve that is not only through the use of brushless DC motors, which are very efficient motors compared to like brush DC motors and stepper motors for higher precision performance, but also to enable 48 volts as a way to get higher power. 48 volts is a quarter of the current, and this can save on a lot of things like having thinner wires so you don't get as much RDS(on) loss through those wires, and switching losses in MOSFETs and all of those things. And as you see robotics across a wide span of voltages from 12 volts to 48 volts and even up to over 100-volt systems, a lot of these systems all have the same challenge of being as efficient as possible. So no matter the voltage, it's always important to think of robotics needing smarter power so that you can get the most efficient optimal systems, whether it's a battery or a line power system.
So going to 48 volts makes a lot of sense to me. You know, higher voltage means lower current for the same amount of power, which is going to be even like less cable loss. And like you said, lighter cables is a good thing for robotics, I imagine. Can you describe some of the other things that make 48 volts really attractive for robotics designers today?
Yeah, absolutely. So 48 volts offers a lot of different advantages compared to traditional 12-volt systems. So 48 volt requirements are really good to support more loads at the same amount of power that you may have had on a 12-volt system, because you are going to require things like higher payloads or higher motor speeds, depending on the application. So 48 volts just gives you that flexibility to open up opportunities for more torque and more speed, especially with a lot of these robotics applications requiring large payloads of up to like 50 kilograms. You want to ensure that you have the power needed to deliver that capacity for these demanding tasks. Also, it gives you opportunities to minimize your radiated and conductive electromagnetic interference, because a lot of these 48-volt drivers offer things like adjustable gate current so that you can really fine-tune your system based on your needs. And most importantly, a lot of these 48-volt drivers have things like integrations for lower BOM costs, as well as system reliability and robustness, so that you can have functionally safe systems that not only support high or low transients in your system, but also give you different types of diagnostics and protection so that you can meet some of robotic standards like ISO and IEC standards.
I guess for the same amount of power, a higher voltage also with the lower current means less loss in long cables too. So you save some power there, I imagine.
Correct. Yes. Less losses in the cabling, and it allows you to really reduce your system cost overall by using thinner cables or thicker AWGs, basically.
So as people are starting to adopt and maybe look at refreshing their systems, can you talk me through the different sorts of architectures that are out there and the advantages of each of them?
Yeah. So, in a lot of these robotics applications, you'll find three-phase brushless DC motors because, from what we talked about earlier, they're efficient, they have longevity, they have different ways you can control them for different speed, torque, or position-based applications. And so, when you're looking at robotics design, there's two different types of architectures that can really help meet your design needs depending on what you're looking for. Traditionally, a lot of people like to look at three-phase BLDC gate drivers because there's 48-volt gate drivers, but an architecture that is pretty useful for these robotics applications is using half-bridge gate drivers. Half-bridge gate drivers control a high side and a low side MOSFET. And by taking three half-bridge drivers, you can actually place these half bridge drivers on a PCB that typically has the motor mounted to it. So if you place the half bridge driver next to each phase of the motor, you can really start to eliminate the signal trace length for gate drive signals from the half bridge driver to the high side and low side MOSFET. What this does is this reduces your length and reduces your overall parasitics that usually cause a lot of switch node ringing or overshoot or ringing kind of phenomena that affects hardware designers. So this type of layout allows you to improve your signal integrity and achieve low propagation delays. On the other hand, you can do a three-phase driver approach where if you have a three-phase driver routing to three phases or six MOSFETs around the PCB, this is more integrated, so you get a lower overall BOM cost, but then you have to care about the ringing and parasitics that may occur from longer gate drive traces around the PCB. So there's a trade-off of, do you want to have an easier routing and better performance for a higher BOM cost, or do you want a lower BOM cost, but then you have to look at some of the transients that may occur, and is your three-phase driver equipped to handle those transients? So it's up to the system designer overall and how they want to design the system.
Can you describe to me the effects of ringing? I imagine there's always a little bit of this. MOSFETs are just kind of
Yes. So
you get what you get sometimes. Yeah.
Yeah. So when you're switching a inductive load, like a motor phase, for instance, you basically have currents that are going in and out of the phase rapidly. So when you're switching MOSFETs, high side or low side MOSFETs at a pretty fast PWM frequency, what can happen is the switch node that is between the MOSFETs connected to the motor phase can start to oscillate because you are either turning on the MOSFETs or turning off the MOSFETs very quickly. So there's different hardware techniques that you can do to eliminate the ringing, such as lowering your gate drive current or adding RC snubbers to the MOSFETs. A lot of useful ways that you can eliminate that, but depending on hardware experience, you might not need any of those extra components if you use a half bridge driver approach, for instance.
Interesting. My reflex before this moment would have been, yeah, half bridge is probably not as good, but
that's interesting. It's interesting. You'll see in the market some different ways to design and different portfolio offerings for this.
One of the things that, as I was reading up on this, as you mentioned gate drive current, the ability to change slew rates was a really interesting thing that I saw. Can you talk about why someone would care about the slew rate of their gate drive?
Yeah, great question. So the MOSFET slew rate is how fast does its drain to source voltage switch. So when you're looking at a MOSFET drain to source voltage, if you're measuring the voltage across that MOSFET, it will go from your battery voltage to 0 volts and vice versa in a certain amount of time. Now, that slew rate can cause a lot of things depending on your system. If you're switching it too fast, it can cause higher EMI. Or if you're switching it too slow, it can result in thermal dissipation and power inefficiency. So controlling your slew rate is optimal depending on your design requirements. So the best way to control slew rate is to control how fast are those MOSFETs switching, which is your gate drive current. So gate drive current is a really nice feature to have in a driver IC, whether it's a half bridge driver or a three-phase driver. And specifically, if you have an adjustable gate drive current, then you can control either via hardware settings or SPI, for instance, how much gate drive current do you want for those MOSFETs. And the whole point is to control the MOSFET switching and the Miller plateau. Long story short, having adjustable gate drive current allows you to control the slew rate of a MOSFET.
So basically, the faster or the more current you drive into the gate, the faster the slew rate up to a certain point.
Yes. The higher the gate drive current, the faster the slew rate, and it depends upon the MOSFET's gate to drain capacitance, or what we call its QGD value. These are in nanocoulombs, and traditionally 48 volt MOSFETs are these really big FETs that come in these really inductive heavy packages that have a lot of capacitance associated with these packages. But as we've seen 48 volt technology start to get better from the MOSFET side, we start to see these QGD values get smaller. We go from hundreds of nanocoulombs down to tens of nanocoulombs, and you don't need as much gate drive current to switch on or off these MOSFETs. So by having a wide range of gate drive current values that you can configure and adjust in your IC, the more flexible your system is. And also, if you can have different timings of how you want to drive your gate drive current, you can also start to control that MOSFET's Miller plateau so that the Miller plateau, which is when the slew occurs, is reduced to a minimal amount of time so that you can get the highest efficiency.
So the Miller plateau is like going from 0 up to your battery voltage. It's that.
Yeah. So the Miller plateau is going to be your MOSFET's gate to source voltage, or VGS. When that MOSFET's gate to source voltage goes from 0 volts to its Miller voltage, that is when the drain to source voltage, or VDS, starts to actually slew, and you get your MOSFET slew rate. This is when current is switching into the FET and going into the motor. So if you can control that Miller plateau through adjustable gate drive current, you can drive a wide variety of 48 volt MOSFETs ranging in QGD values.
How do you actually go about adjusting that? Is that like a like a register you burn or something? Like how do you
there's many different techniques based on the IC. You can have it traditionally as serial peripheral interface, or SPI. You have registers that you can configure and tune for your application. Sometimes there are devices where you can just set a single resistor to choose your gate drive current setting. So it depends on the driver itself.
Yeah, I've seen people from like an EMI signal integrity perspective kind of like detune their switching FETs a little bit so that they're not all right on the same frequency and causing a big RF spike. They've kind of smeared it across the spectrum to keep it under the like FCC thresholds.
Yep, and it can depend on how your board is laid out, on your EMI requirements that you're trying to meet. Lots of different things can dictate how an engineer wants to tune their gate drive current.
Shifting gears a little bit back to safety, can you go into a little more detail about some of the different types of specifications and which ones people might want to consider for their own designs and which ones maybe don't apply to them?
Yeah, so in robotics, there's a lot of different safety ratings and a lot of different regulations that are defined by various different organizations, so that no matter the type of robotics application, whether it's a home robot to an industrial mobile robot to something very safety oriented like a humanoid, there's a wide range of standards that are in place today. So many of these standards, such as UL 2595 or ISO 13484, going all the way to the most stringent standards like IEC 61800, a lot of these different standards are good suggestions for electronics to build safety in their devices, so that when it comes to looking at system safety levels to meet these standards, these ICs help engineers do a lot of that safety for you. It comes with diagnostics, protection, and many different things along the lines of SIL 2 or SIL 3 level of standards, so that when an engineer has to design and verify the design that is operating safely, the ICs help the engineers do most of that for them. So you're cutting down design time, you're making a very valid safety case so that there is no risk and that these robotics applications serve for a long time in the market, even in the most harsh environments.
What sorts of things are being tested from a safety perspective? Is it like over voltage conditions or, conducted resilience? What sort of things are being looked at?
Yeah, so traditionally, diagnostics and different types of protections in a motor driver are things like over voltage, under voltage, over temperature, making sure that your components that are outside of your motor driver, such as the MOSFETs, drain to source voltage or gate to source voltage, or even if there's current sense amplifiers integrated, you want to make sure that all of your components in the system has a way of being protected. So traditionally, these motor drivers will incorporate these protection mechanisms and diagnostics to make sure that these applications all work as intended. But more importantly, another level of diagnostics is you want to make sure that the diagnostics that you have in your device are going to work. So you have to check itself essentially, right? How do you know that your driver is actually going to shut down correctly if you see an overcurrent or over voltage condition? So it's important that engineers think about different diagnostics to make sure that their devices are working. And if you have a driver that doesn't do that, well, guess what? You're going to be spending extra BOM costs on different types of comparators or circuits externally to ensure that your system is safe. So why not have an IC that does all that for you? So that's the extra level of diagnostics and protection you can have in a driver.
And that's the whole point of having an IC, is to not have to do a bunch of discrete things yourself, right?
Exactly. Yeah. Integration is key.
Talking about safety, it's great to get the label, to get the sticker, the approval. What other sorts of things should people be thinking about for safety, and how much should they be checking these things themselves?
Absolutely. So safety is more than just diagnostics. You want to be able to verify and validate that your system is working in the most harsh conditions or environments, depending on your application. You can have other types of noise or other types of battery conditions or line voltage conditions that can affect your system, or you may have motor conditions that can cause like load dumps and all these other various things. You want to be able to verify that your system is meeting the design requirements it was intended to do so, and you want to validate that the system works in all of these real world conditions. So it's important that the system is, capable enough to be able to ensure that all of your diagnostics function correctly, like I mentioned earlier, but also that you can test all of your different loads and speeds and environments by validating how that works with your IC. And by having all of these protections and mechanisms internally, it makes it easier to comply to different standards and to have performance and reliability in your system.
So the label, the safety label is always a good thing to have, but it's important to make sure it works for you and your systems as well. That's kind of what you're saying.
It's exactly, yeah. You want to make sure that the system does not have any risk of not operating the way it should. Yes, it's easy to design for cost, but most of these things like safety aren't usually really thought about until later on in the application if it's not identified earlier. So having an IC that comes equipped, ready to go to make the safety case easier to implement is always a preferred solution for engineers.
Without naming any names, can you share any of the more interesting or dramatic failures you've seen on the robotics side? I'm sure you've heard some interesting stories.
Yeah, I haven't worked personally in like a robotics factory, but from some of the different horror stories I've heard as a former applications engineer myself, it's easy to have shoot-through conditions in MOSFETs where you apply some sort of large external load or force, or let's say in a robotics application, you're just picking up a really heavy package, right? And that sudden change in torque or force can cause a large amount of current and spiking that occurs in the MOSFETs. That spike can cause a shoot-through condition through the MOSFETs, and boom, you can have ICs exploding, failures in the field, and all of a sudden you have to diagnose why that's the case. Rather than seeing blown up parts and blown up PCBs, it's better to have all this like tested beforehand using different diagnostics and safety features so that You don't have to have field failures.
When it comes to avoiding field failures, I know avoiding that is top of mind for the Allegro designers. So, can you tell me more about the half bridge gate drivers you have?
Yeah, absolutely. So as I mentioned earlier, half bridge drivers can really help with system design in terms of eliminating gate drive trinks legs. So Allegro offers a wide variety of half bridge drivers for robotics applications that are true 48 volt drivers, meaning the absolute max is 80 volts. And you can control really high QG MOSFETs, such as putting MOSFETs in parallel or driving really powerful FETs so that you can drive these large payloads. Our half bridge drivers can be very protected, such as the AMT 49502 and the A89503. These drivers have SIL 3 compliance. They have extensive diagnostics for these harsh environments and can support up to negative 18 volts transients and have wide varieties of integration, including charge pumps and different types of protections and monitoring pins. We also have a really small driver called the 89500 that is 3 by 3 millimeters squared and can drive really powerful FETs. And you can have it in a very small form factor with functional safety quality managed protection. So this can be for really robust small applications like joints and arms and things that don't require as much functional safety as more integrated half bridge drivers.
Is thermals an issue at that sort of footprint? Because that's really small.
Yeah, very small, and that's where the system may depend on, what kind of gate drive current do I need in order to switch those FETs, right? So you might have a more discrete architecture because you're saving the money on the smaller ICs. It depends on if you want to do your gate drive current adjustments integrated into the device, or maybe use a gate resistor or something a little bit more discrete. But the options are available for the designer to choose.
Can you also tell me a little bit about what Allegro offers on the BLDC three-phase side?
So Allegro offers three-phase brushless DC gate drivers for 48 volt robotics. The two devices that we have are the AMT 49100 and the AMT 49101. These are true 48 volt brushless DC drivers that can drive up to 80 volts apps max and can also drive a wide range of MOSFETs because of the high gate drive current capability that these MOSFETs have. And these are BLDC drivers, right? So they come with a variety of integrations and protection mechanisms. So for instance, from a safety perspective, these devices can be up to SIL 3 compliant for those types of robust robotic systems. And they have transient supports of up to negative 18 volts. So if depending on the system design that we talked about earlier, if you have transients on the battery or on the ground, these devices can survive those transients. We also offer integrations like a buck regulator, charge pump, 3 low side current sense amplifiers, all inside of a small 7x7 millimeter package.
What sort of eval kits or samples are available? Because I have a whole box of dev boards over here, and maybe I need one more.
Yes, so you can find a lot of our eval boards on our product pages. So every product page has an eval board that you can order and samples that you can order on the website, as well as documentation helpful for evaluation.
The website for that is mauser.com/allegro-robotics if people want to go check out more. Any parting design advice or caveats for people who are starting to implement these for the first time?
Yeah, so don't be afraid when designing 48 volt robotic systems to find ways to save efficiency and power and safety needs for the long term, right? There might be pressure to try to save as much money as you can on a 12 volt system. But if you think about the future, right, a lot of the things you need to enable a 48 volt system is already here for you. Ways to evaluate, ways to design more optimally with a half bridge driver or a 3-phase BLDC driver. We have many support resources as well to help assist you with 48 volt design. So don't be afraid to make a big change to a system if that's what's needed to get you the most efficiency.
Great advice. Well, thank you so much for your time and for being here. This was really interesting.
Yeah, thank you very much. I appreciate it.
You can find the Allegro Microsystems devices and dev kits we talked about today and a lot more from them at mauser.com/allegro-robotics. Thanks to Mauser for sponsoring this tech chat. I'm Daniel Bogdanoff, and I'll see you next time.